Alright folks, here is video 2 from section 5.1, working with radicals. And we're going to talk really quickly here about working with radicals, writing radicals in simplest form, which is something we've already actually done. We just didn't specifically say that's what we were doing. Basically, in the last video, when we took an entire radical and wrote it as a mixed radical, we were putting the radical in simplest form. Okay, so our rules for a radical in simplest form is the following. The radicand does not contain a fraction. So you cannot have fractions underneath your radical sign. So no radicands that are fractions. And it also can't contain any other factor which may be removed. So if you think back to the previous example, we took that 48 and we wrote it as 16 times 3. So we could pull out 16 as a perfect square from the radical sign. And we'll do that here in a second with the 18. The second rule is a little bit strange, and we'll talk about it as well. It says the radical is not part of the denominator of a fraction. So it's not proper, it's not mathematically incorrect if you write it in the denominator, but it's not a proper form to have the radical as a denominator. Okay, so let's start with their quick example here, square root of 18. So square root of 18 is an entire radical. And basically what we're going to do is 18 we can write as a product of 9 and 2. So this is the square root of 9 times 2. Since 9 is a factor I can pull out of the radical sign because it's a perfect square. This is the square root of 9 times the square root of 2. And the square root of 9 is 3. So 3 root 2. In simplest form, the square root of 18 would be 3 root 2. So that's one example of putting a radical in simplest form. The other one that I want to look at is what happens when you have the radical in the denominator. And we're going to do more with that in the coming sections, but just because it's mentioned here, I want to talk about it. So if I had something like this, if I had, let me change colors so that it's clear it's a different example. If I had 5 over the square root of 3. Okay, so 5 over the square root of 3, this is not a proper way to have your radical. So what we need to do is we need to scale this in such a way that it gets rid of the square root on the bottom. And what that winds up looking like is this. We're going to multiply. If I want the square root of 3 to not be a square root, well, the square root of 3 squared would be 3. And to square the square root of 3, I'm going to multiply it by itself. So I'm going to multiply the top and bottom of this fraction by the square root of 3. What that's going to do is on top, I'm going to wind up with 5 root 3. And on the bottom, square root of 3 times the square root of 3 is 3. So in simplest form, this would be 5/3, or 1 2/3. Times the square root of 3. So our coefficient is allowed to be a fraction, but we're not allowed to have a fraction in our radicand. Okay, so we have fixed that. And again, this is something we're going to look at more in section 5.2. Okay, so simplest form, pull out anything that you can from underneath the radical sign, no fractions underneath the radical sign, and the radicand, the radical, is not part of the denominator of a fraction. Okay, so let's compare and order radicals. This one, and we're going to do this, it says without using a calculator. What they really mean by without, you can use a calculator to help with some of it if you want. But what they really mean is you're going to have to be able to say which is the least and which is the greatest without just plugging it into your calculator and getting a decimal value. Okay, and what we're going to do to compare these is we're going to express them all. I'm going to go back to green. We're going to express them all as entire radicals. Okay, so to compare, express all as entire radicals. Okay, and once we've done that, we're going to be able to compare them and order them. Okay, all right. And it says just the context for the question. It says 5 bentwood boxes, each in the shape of a cube, have the following diagonal lengths in centimeters. So these are the lengths of the diagonal in these boxes. Anyway, so Pythagorean theorem would come into play here. Let's just order them. Okay, so 4 times 13 to the 1/2. 13 to the 1/2, remember. So 4 times 13 to the 1/2. 13 exponent 1/2 is just another way of writing the square root of 13. So we're going to write this guy. Actually, maybe I'll work my way down. That's probably going to be more user-friendly here. 13 to the 1/2 is just the square root of 13. So this is really 4 times the square root of 13. If I want to bring the 4 underneath, I need to write this as a whole radical. So that's going to be 4 squared is 16. So this is going to be the square root of 16 times the square root of 13. Put them together, and that's the square root of 16 times 13. So I will forgive you at this point if you reach for a calculator to do 16 times 13. And that's 208. So this simplifies to the square root of 208. So that's our first one. 8 root 3, second one. 8 square root of 3. 8 is the square root of 64, so root 64 times the square root of 3. Square root of 64 times the square root of 3 is the square root of 64 times 3. And that's going to be 192. I'm going to check that. 64 times 3. Yeah, 192. Why would I ever doubt myself? 192. Yeah, so already, now that we've expressed these as entire radicals, we can see that 4 times 13 to the 1/2 is larger. That would be a longer length than 8 times root 3, because the square root of 208 would be a larger number than the square root of 192. Okay, 14. 14 is mercifully easy. If I want to write 14 as a radical, I'm just going to, well, 14 squared is 196. So 14 is the square root of 196. Okay, so once again, because 14 squared equals 196, I can do that. Square root of 202, I don't have to do anything with. That's quite thoughtful of them. So the square root of 202 is the square root of 202. And last but not least, what color haven't I used? Purple. 10 root 2. Okay, so 10 root 2, actually you might remember that one. We did that one the other day as an example. 10 root 2. We're going to write 10 as the square root of 100. Okay, because the square root of 100, 10 squared is 100. So 10 is the square root of 100. So this equals the square root of 100 times the square root of 2 is, and you're probably, I'm showing this middle step here where I'm going to write it as the square root of 100 times 2. If you skip straight to the square root of 200, I think you can be forgiven. So those are our numbers, and they want them in order from least to greatest. So that means in terms of least, that was 8 root 3, square root of 192. So least 8 root 3 followed by 14 followed by the square root of 200 was 10 root 2 followed by square root of 202, and then greatest in this case was 4 times 13 to the 1/2. And hold on there, let me fix that. 13 to the 1/2. Least to greatest. All right. And again, you're welcome to use a calculator to do some of the interim parts. But if you're asked to show your work as to how you got which was the least and which was the greatest, you've got to express them all as entire radicals, and that would be required if this were on a quiz or a test. All right, I'm going to stop video 2 here because so far it appears it's under 10 minutes, barely, and I will talk to you again in video 3 the last video for this section.